First problem says, use the Maclaurin series 1 over 1 minus x is equal to the sum of k from 0 to infinity of x to the power of k to find the Maclaurin series for the following. In each case, write down the terms of the series up to x to the power 4. So what we can do is just manipulate this expression to get the expression in each of these parts, and then whatever we change to this part, we have to change to this. So for a, we can change this x to an x squared, so substitute x squared for this x. So 1 minus x squared. And whatever we change to this part, we have to change for this part. So since we substituted x for x into here, that means we have to substitute x squared for x into here. So sum k equals 0 to infinity of x squared k. And then now what we can do is just write down each of the terms. So starting from k equals 0, it's x squared to the power of 0, so 1 plus k x squared plus k equals 2 is going to be x to the 4th plus x to the 6th, or this term, we don't need it because it's just up to x to the 4th. So that's your answer for part A. For part B, we do something similar. We can substitute negative x for x because this changes from 1 minus x to 1 plus x, so we just change this the sign of the x. So 1 over 1 plus x is equal to sum from k equals 0 to infinity of negative x to the power of k. And then we write the first terms, so when k equals 0, it's 1, and then when k equals 1, it's negative x. When k equals 2, it's x squared. When k equals 3, it's minus x cubed. And when k equals 4, it's x to the 4th. So that's your answer for part B. For part C, you do the same thing. You substitute 2x for x. So this is the same process. So from k equals 0 to infinity of 2x to the k. The first few terms will be 1 plus 2x plus 2x, 4x squared plus 8x cubed plus 16x to the 4th. So that's the answer for part C. In part D, you can actually use part B for your answer in part D. If you don't have it written down, you should have it written down. It's 1 minus x plus x squared minus x cubed plus x to the 4th for part B. And D is just that multiplied by 2 because 1 times 2 is 2. So 2 minus 2x plus 2x squared minus 2x cubed plus 2x to the 4th. And that's your answer for part D. The second problem says, use the Maclaurin series cosine x equals the sum from k equals 0 to infinity of this to find the Maclaurin series for the following. In each case, write down the terms of the series up to x to the 6th. So since this summation thing is kind of complicated and there's a lot of things going on, just write out the terms of the series of cosine x up to x to the 6th first, and then we can manipulate that. So, and this is actually in your format booklet as well, I think, so you don't even need to do this manually. So it's going to be 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and so on. So for a, cosine 2x, you just replace x with 2x. So 1 minus 2x squared, 4x squared over 2, and that is just 2x squared plus 2x to the 4th is 16 x to the 4th over 24, and that is 2 over 3. You can simplify it to that. Minus 2x to the power of 6 is 64 x to the 6th over 6 factorial 720. And this could be simplified to 4 over 45. And yeah, those are your terms for part A. And for part B, you replace x with negative x. So 1 minus x squared over 2. This term is going to stay the same because negative x squared is the same, plus x to the 4th over 24. This term is going to stay the same as well, minus x to the 6th over 720. So all the terms stay the same. So those are your answers for part A and B. And for part C, it's the same. You just replace x with x squared. So 1 minus x to the 4th over 2 plus x to the 8th over 24. And you don't even need that term because it's past x to the 6th. So it's just 2 terms for part C. And then part D, you multiply the entire thing by x because if you think about it, like if you multiply cosine x by x, then you have to multiply this entire thing by x. So it's going to be x minus x cubed over 2 plus x to the 5th over 24, and you don't need the last term, or you do need that term, but you don't need the term after that because it's going to be greater than x to the 6th. So this is part C, this is part D. Those are your answers. So now let's find the Maclaurin series for each of these because we still need to find the sigma notation for all of them. So for the first one, cosine of 2x. 1 second. So 2x, we replace the x with 2x again. And then you should make it like 2 to the power of 2k times x to the power of 2k. And what you can do is you change the 2 to the power of 2 to 4 to the power of k. And then you can move the 4 to the power of k into the negative 1 to the power of k. So this becomes negative 4 to the power of k time. And then this is your final answer for part A. And then for part B, you replace x with negative x. And then you should factor out the negative 1 like that. And whenever you have negative 1 raised to an even power, it's always going to be 1. So it doesn't do anything. So for B, it's going to be the exact same. It's just going to be this. And for cosine of x squared, replace this with x squared. And then the squared goes into 2, so this becomes 4k. That's your answer for part C. And then for part D, you multiply the entire thing by x, which is because it's x cosine x. And then the x goes into the sigma notation and goes into this x raised to what power. And you just add 1 like that. And that's your answer for part D. So question 3 says, using the Maclaurin series, sine x equals the sum from k equals 0 to infinity of this. Define the Maclaurin series for these. And the question says find the Maclaurin series, and it doesn't say like write the first few terms or write the terms up to whatever. So your answer is going to be in sigma notation, just like this right here. But it's still the same process. You just substitute, like for part A, you substitute negative x for x. And it's going to be like sigma notation, k equals 0 to infinity of negative 1 to the power of k over 2k plus 1 factorial times x to the 2k plus 1, or actually negative x to 2k plus 1. And make sure that the 2k plus 1 gets factored into both the negative 1 and the x. And also, this can be simplified because you should know that negative 1 to the power of 2k plus 1 is negative 1 to the power of 2k times negative 1 to the power of 1. And whenever negative 1 is has an even power, like 2, 4, 6, 8, it's always going to be 1. So we can just get rid of this 2k because it's not doing anything. So it's negative 1 to the power of 1, which means that the negative 1 to the power of k here can just be turned into k plus 1. And then imagine this is more to the left. I'm too lazy to redraw it, but that's your answer for part A. For part B, you substitute 3x for x, so it's going to be from k equals 0 to infinity of -1 to the power of k over 2k plus 1 factorial of, and then 3x to the power of 2k plus 1. And this can't really be simplified, so that's the answer for part B. For part C, you substitute x squared for x, so it's going to be from k equals 0 to infinity, -1 to the k of over 2k plus 1 factorial. And then instead of x, is going to be x squared, so x squared 2k plus 1. And you can just change that to 4k plus 2. So x to the power of 4k plus 2. And this can't really be simplified, so that's our final answer for part C. So for part D, you just multiply sine x by x, and if you have an x in the front here, that means you need to multiply the other side by x, and you can just move that x inside this segment notation. So this x to the power of 2k plus 1 will be changed to x power 2k plus 2, and that's our final answer. So question 4 says use the Maclaurin series e to the x equals the sum from k equals 0 to infinity of this to find the Maclaurin series for the following. In each case, write down the terms of the series up to x to the fourth. So e to the x is in your formula booklet, so I would recommend writing down all the terms first. And even if you don't have your formula book right now, you could just write down the first few terms. So it's 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the fourth over 4 factorial, and so on. And for part A, just replace x with 3x. So 1 plus 3x plus 9x squared over 2 plus 27x cubed over 6. And that can be simplified to 9 over 2 plus 81x to the 4 over 24. And I don't think that can be simplified. Oh, it can. Yeah, 27 over 8. So that's the answer for part A. So for part B, it's also simple. You just substitute x squared for x. So 1 plus x squared plus x to the fourth over 2. And the next terms are going to be greater than x to the fourth, so you don't need them. So this is the answer for part B. And then for part C, you can see it's not really written in the form of e to the x or e to the something. What we can do is rewrite it as e to the ln of 2 to the x, because that's equivalent. And then you move that x to the front here, e to the x ln 2, properties of logs. And then you just substitute x ln 2 for x. So 1 plus x ln 2 plus x squared ln 2 squared over 2 plus x cubed ln 2 cubed over 6 plus x to the fourth ln 2 to the fourth over 24. So that's your answer for part C. And now let's find the Maclaurin series for both in segment notation. So for part A, you replace x with 3x. So this becomes 3x to the k, or x to the k times 3 to the k. That's the answer for part A. And for part B, replace x for x squared for x. So this becomes x squared to the k, or x to the 2k. And then all this becomes your answer for part B. And then for part C, remember we wrote that 2 to the x is equivalent to x ln 2. So you replace x for x ln 2, which is just x to the k times ln of 2 to the k. And that's your answer for part C. So number 5, part A says use the Maclaurin series sin x equals the sum from k equals 0 to infinity of that to find an infinite series representation for sine of x plus pi over 2. So for this one, again, you just substitute something for x, and in this case, you substitute x plus pi over 2 for x. So it's just, I'll write here, sine of x plus pi over 2 is equal to the sum from k equals 0 to infinity of -1 to the k over 2k plus 1 factorial of x times x plus pi over 2 times to the power of 2k plus 1. Yeah, so that's part A. And part B says use the binomial theorem to write out the terms of the series up to x to the 4th. Explain your result. So the first thing you need to do is use sigma notation from part A to rewrite sine of x plus pi over 2, just write the first few terms of the Maclaurin series. So it will be pi over 2 plus x minus pi over 2 plus x cubed over 3 factorial plus pi over 2 plus x to the 5th over 5 factorial minus pi over 2 minus plus x to the 7th over 7 factorial, and so on. And this is where you use the binomial theorem. You use the binomial theorem to expand out your binomials, and then after you do that, you're gonna get to this first part. I didn't feel like writing all of it out because it's pretty long, but you're gonna get to this first part. There's not much to explain, you just kind of do it, use the binomial theorem, and then after that, to get to the second part, this part, what you need to do is you want to rewrite it so that you can get something out of it. You can rewrite it so that you can get a series, and you can rewrite it in sigma notation. And to do that, you can try regrouping all of the terms based on what power the x is raised to. So first, you take this term, pi over 2, this term, and this term, and then all the infinite beyond, and then you get all of these. And these are all the terms where x is raised to the power of 0 because there's no x's. And then you take the terms where x is raised to the first power, so this one, this one, this one, and this one. And then again, don't forget to put the factorials at the beginning of your term. So it's going to be just these 4, and then you're going to get something like this. And you can factor out the x, so you just put these inside your parentheses. And then again, the next one, for when x is raised to the power of 2, there's nothing in here, so you just start here, and then yeah, you go on. So now you might be able to see a pattern in these. This is equivalent to this, and this is equivalent to this. So every odd regrouping is the same, and every even regrouping is the same. And every odd regrouping is actually equivalent to sine pi over 2, because this follows the same pattern as sine of x, except for that x is replaced with pi over 2. So we can rewrite these as sine of pi over 2. So and sine of pi over 2 is just what? 1. And then these, pretty similar. This is cosine of pi over 2. because it follows the same pattern as cosine of x, with x replaced with pi over 2. And cosine of pi over 2 is just 0, so we just skip all the odd terms, actually, and we only write the even ones. So yeah, it's going to be 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, and so on. And this is all we need. We've already simplified it a lot, and you should be able to tell now this is just the expansion for cosine of x. And yeah, so that's our answer. And to explain our result, this is our result. To explain it is because sine of x plus pi over 2 is equivalent to cosine of x. And that kind of checks out because once we rewrote everything, expanded it out, simplified it, we got this, which is equivalent to cosine of x, which like checks out with it being equal. So yeah, that explains our result. So number 6, part A says use the Maclaurin series expansion for e to the x to write down expansions for these functions. And I already wrote down the first few terms of e to the x. This is in your formula booklet. And then you can derive the sigma notation easily from that. And then for all of these parts, you just plug in whatever you need for x, whatever in place of x. So for e to the negative x, it's equal to 1 minus x plus x squared over 2 plus x cubed, or minus x cubed over 6, and so on. And then the sigma notation. And when we do the sigma notation, we don't have to look at the first few terms that we've written out. We can just use the sigma notation from here that you derived from e to the x originally. So it's going to be k equals 0 to infinity of negative x to the k over k factorial. And again, you can factor out the negative 1 to make it clear that it switches signs every time. So that's your answer for part A, part 1. Part 2 says e to the negative 3x, and we can use part 1 for this because e to the negative x is closer to e to the negative 3x than e to the x is. So we just replace negative x with negative 3x, and then we change this x to minus 3x, this x squared into 9x squared, and this x cubed into 27x cubed, and this can actually be simplified into 9 over 2 x cubed. So those are your first few terms, and for the sigma notation, you just replace this x with 3x, and yeah, that's your answer for part 2. Part 3 says e to the negative 2n plus 1x, and again, we can use part 1 for this. I'll write it right here. So we have part 1 right here, and then e to the negative 2n plus 1 x is equal to 1 minus 2n plus 1 x plus 2n plus 1 squared x squared over 2 minus 2n plus 1 cubed x cubed over 6, and so on. In the sigma notation, we plug in negative 2n plus 1x for x, as always. So k from 0 to infinity of negative 1 to the k times 2n plus 1 k x k over k factorial. And that's your answer for part 3. So part B says, use the Maclaurin series expansion for sine of x to find the first two non-zero terms of the Maclaurin series expansion for sine of e to the negative x. So first, let's write out sine of x, which is equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and so on. This is in your formula booklet. And then you replace x with e to the negative x. So sine e to the negative x is equal to e to the negative x minus e to the negative 3x over 6, or let's leave that 3 factorial, and then plus e to the negative 5x over 5 factorial, and so on. So yeah, and we can replace these e to the negative x, e to the negative 3x, and e to the negative 5x with formulas for the Maclaurin series that we found in part A. And as you notice, as each term progresses, they actually follow the pattern of negative 2n plus 1 of x, such that n is an integer. So yeah, so for e to the negative x, it's 1 minus x plus x squared over 2 factorial, so on, then minus 1 over 3 factorial multiplied by e to the negative 3x, which is 1 minus 3x plus 9x squared over 3, or 2 factorial, minus so on. And then for the nth term in this expansion, it's going to be like, we can see just from the first two that the sign switches every time, so we'll have a negative 1 to the k, and we can see for the first two terms, or just this sine x expansion in general, that the factorial on the bottom increases by 2k plus 1, so 2k plus 1 factorial, and then in the parentheses we have our e to the negative 2k plus 2k times x. So we can just insert this thing, 1 minus 2k plus 1 x plus 2k plus 1 squared x squared over 2 factorial minus so on. And yeah, we can put this right here again, because again it follows the pattern of negative 2n plus 1 with each following term. And now we need to regroup our terms so that, you know, each group has the same like power of x. And for the first one, we're gonna actually write our first two non-zero terms as summations. So the first one, from k to 0 to infinity, we take up an infinite amount of these first terms, and it's just going to be negative 1 to the k times 2k over 2k plus 1 factorial, because that's at the beginning, and then we just have 1, just multiply by 1 every single time, so we do nothing here. So that's our first term, and the second one is again a summation from k equals 0 to infinity of all the terms where x is raised to a power of 1. So this x, and this x. So again, we always write this at the beginning because it's at the beginning of every single term, or like term grouping. And then our pattern for x is literally given right here, so we just write that in 2k plus 1 and then multiplied by x. And then those are our first two terms. That's our answer for part B. And this should actually be subtraction, because each term where the x is raised to the first power, it's minus 2k plus 1, so subtraction, therefore negative. And you can notice that 2k plus 1 over 2k plus 1 factorial, you can factor out a 2k plus 1 out of both the numerator and the denominator, so this 2k plus 1 gets removed, and the denominator gets turned into 2k factorial. So yeah, that's the answer for part B. Part C says, hence find an approximation for sine of e to the negative x for x near 0. And when x is near 0, that means that, because we only wrote the first two terms, but as we write more terms, the x is going to increase to x squared, x cubed, x to the fourth, and when x is near 0, that means all the future terms approach 0 as well. So we should only focus on these two terms that we wrote to find an approximation. And what we can do is just write both of them out, like write the first few terms of each one. So for the first one, let's just write a few terms. So it's going to be -1 to the power of 0. So 1 over 2 times 0 plus 1, so 1. And then minus 1 over 2 times 1, 3 factorial, plus 1 over 2 times 2 plus 1, 5 factorial, and then so on. And this is actually just the Maclaurin series for sine of 1, because, you know, like the 1, even though it just stays 1 on top, this is technically 1, 1 cubed, 1 to the 5th, and that's just the pattern that sine of x follows. And then now let's do the second one. So let's ignore this x for now. So let's just ignore it. And then it's going to be 1 over 2 times 0 factorial. So 1 minus 1 over 2 factorial plus 1 over 4 factorial, and so on. And this is the same. This is just cosine of 1. It follows the same pattern as cosine of x, just like I explained for the first one. So now we can rewrite this as sine of 1 minus cosine of 1 times x. And that's our approximation for sine of e to the negative x. Part D says, find by direct calculation the Maclaurin polynomial of degree 2 of sine of e to the negative x. And Maclaurin polynomial of degree 2 just means write out the Maclaurin series until x squared. And this is how we're going to write our notation. And then first we need to find out f of 0, assuming this is f of x. And sine of e to the negative 0 is just sine of 1. So that's the first term. And then we need f prime of x, which is cosine e to the negative x times negative e to the negative x. And f prime of 0 is cosine times cosine of e to the negative 0, which is cosine of 1. And negative e to the negative 0 is just 1, or negative 1. So it's going to be sine of 1 minus cosine of 1 times x. And then now we need to find f double prime of x, which is negative sine of e to the negative x times negative e to the negative x times negative e to the negative x again, which is, so negative e to the negative x squared, plus cosine of e to the negative x times e to the negative x. So, and now we find f double prime of 0 equals negative sine of 1 times negative 1 squared. So that just keeps negative, plus cosine of e to the negative 1, negative 0, which is cosine of 1, and e to the negative 0 is 1. So that is our second derivative of 0. So sine 1 plus cosine 1 of times x squared over 2 factorial. Yeah. And then we should actually change this to minus. But yeah, that is our Maclaurin polynomial of degree 2 for part D. That's your answer. And notice how these first couple terms, sine of 1 minus cosine of 1x, is what we derived for our approximation in part C. So that kind of proves that our approximation was correct.